Hi, good morning to everybody. So we have come to the last day of this exciting ASI conference. So we have four plenary talks in the morning and poster session, and later in the afternoon parallel sessions. No? So let's start with the first of these plenary talks by Prajwal Banerjee. So he have the title there, Rapidly Rotating Massive Stars as a Source of High Carbon and Heavy Elements in the Early Universe. Please go ahead, Prajwal.
Thanks. I would like to thank the SOC for giving me an opportunity to present my work. So first half of the talk is from the thesis work by Gina, and the second half is something I did earlier. So I'll be talking about, as the title suggests, massive stars in the early universe, which can resolve some potential problems with respect to what we see in our own galaxy, in the early galaxy. So what I'll use is what is called stellar archaeology with very metal-poor stars. So these are stars which have very little iron in them, about 100 times less iron. So you can find these stars in our galaxy today, and by looking at them, you can learn about what happened a long time back. So if you go all the way back to Big Bang, is the cartoon. So there would be the first stars that would have formed after a few 100 million years. And the IMF of these stars are expected to be very different from the IMF that we see around us today. So these are mostly massive stars, more than 10 solar masses. They undergo core collapse. Some of them can explode. When they explode, they throw out the metals. That allows the transition from top-heavy IMF to salpeter-like IMF, where you find these low mass stars along with massive stars. And if their mass is less than 0.8 solar mass, we know that the lifetime is more than the age of the universe, so that you can find them today. So these will have very little metals in them. And so again, it's a cartoon of a star. So most of the time you're looking at the surface of the star, and if you look at the composition of the star, it will be essentially unchanged over time because all the nuclear reactions are happening in the core. The envelope remains unchanged, which means envelope is the same as looking back at the snapshot of the ISM at the time they were formed, so within first giga years. So you can get a host of important information. This is something sometimes referred to as near-field cosmology, because you're looking at stars that are in the Milky Way to study things that happen at very high redshifts. So because very few events contribute to this, the formation of the star, you can kind of study individual events. And the individual events we're talking about is obviously the first generation of massive stars and maybe the earliest generation of massive stars as well. And then by studying the composition, you can compare with theoretical calculations to constrain the nature of the first stars and early massive stars. So that is what I'm going to kind of focus on today. You can also get a lot of information out by studying these stars about early galaxy formation, star formation, chemical evolution, etc. These very metal-poor stars which have iron less than 100 times than the sun, are hard to find, but over the last 30 years, due to hard work by observers, several hundreds have been found, maybe more than 1,000. And what we find here is something called carbon enhancement. So we can define nominal carbon enhancement relative to iron, relative to solar, 0.7, so a factor of 5-ish. So what we see is, if we look at the very metal-poor stars that satisfy this criteria, carbon over iron greater than 0.7, their frequency, cumulative frequency, which is on the y-axis, 1 means all of them are carbon enhanced. So they kind of keep on increasing, and you can see below a certain Fe over H of -3 or -4, majority of them are carbon enhanced. And at the very low iron content, they are essentially all carbon enhanced. So this means that as we expect that we go back in time, means a lower metallicity, the early first generation of massive stars must be doing something different to produce this carbon enhancement, okay? So that is about the relative abundance of carbon relative to iron. What about the absolute abundance? So absolute abundance is essentially log epsilon or whatever you're familiar with, number of carbon atoms relative to hydrogen, log of that plus 12. So if you plot that, this is called a Yoon-Beers diagram. If you plot the absolute carbon of very metal-poor stars, so these are stars which have normal carbon. These are all carbon enhanced, meaning satisfying carbon over Fe box greater than 0.7. You form 3 groups, and these 3 groups have, they're colored in red and green. So the green ones are what are called carbon-enhanced metal poor S stars. It's a little confusing terminology. What it means is it has, in addition to carbon, high enhancement of heavy elements. So we will, for now, discount them. They're thought to be from binary evolution, but I'll say something about them in the second part of my talk. But I'll focus on these red circles. These are carbon-enhanced metal poor no star. The no means no enhancement of heavy elements, okay? So these are thought to be bona fide descendants of the first generation of stars or not polluted by binary evolution. So these would be like the snapshot of the ISM. So what you see here is absolute carbon levels in these stars varying from around 2.5 orders of magnitude as you scan the various Fe over H. So 5 to 7.5. Now the question is, whatever the first stars make, in addition to carbon over iron, you have to also produce this level of carbon after you dilute with some hydrogen. So this becomes an important point, as you will see. So before going on further, here's a kind of a cartoon of a core collapse supernova. So this is an attempt, my attempt to explain to you how people calculate models and then fit it to observations. So this is the structure of the star as it is about to collapse. You have the iron core, which is not where the iron comes from. It is going back to form neutron star or a black hole. But you'll have an explosion, core collapse and an explosion. That explosion will create iron here, right around here, okay? What the important thing is that this has this concentric layers of lighter and lighter elements. So the heavier elements are at the center, lighter elements outside. So if you have, depending on what kind of explosion you have, normal, medium, or weak explosion, people have seen that a fraction of the innermost material will fall back onto the remnant, and there will be a preferential ejection of the outer layers. So this apparently was more common in the first stars. So what people have done, obviously the simulations in 3D are very expensive. So it is seen in 3D simulations, but on a large scale what people do is in 1D calculation, they say that a fraction of the material in the inner region will come out, whereas most of the material in the outer region will be ejected. So as you can see, carbon is sitting here, iron is sitting here. You can control the carbon relative to iron by playing with the fraction ejected. So that is what people have done, and what they find is, so this is two works from two different groups. One is the Japanese group, and this is American/Australian group, Alex Heger, Stan Woosley's group. So what they plot is essentially these black circles on the left and the red circles on the right are the observations, and the lines you see are the theoretical predictions. They are slightly different, using slightly different quantities. This is x over Fe, which you are familiar with. This is production factor, same as x over Fe, but not normalized to iron, okay? It's relative to the sun. So what they find is that you can explain the carbon over iron quite well. So if you can control the iron relative to carbon ejection, as I showed you in the last slide, you can fit the carbon relative to iron quite well. So this is kind of resolved. So the only thing is that first stars were mostly having some kind of weaker explosion, which led to this enhancement. So theoretically, we are kind of fine with the carbon over Fe. So the problem comes with the absolute abundance of carbon, okay? So as you know, when a supernova explodes, you cannot just say that my carbon that is ejected by the supernova will just form the next generation of stars without undergoing any dilution. Dilution is a fundamental property of any supernova explosion. You will have dilution, you will have the next generation of star formation, and then you can show that there would be at least a minimum amount of dilution. That would be the amount of mass swept up by the blast wave, supernova blast wave. That's at a minimum that dilution has to a supernova ejector has to undergo, which means whatever you eject will be mixed with at least around 10 to the 4 solar mass of material. You cannot avoid that, okay? It has some scaling with explosion energies. But then you can ask the question, how much carbon can you produce in a supernova, right? It turns out the carbon that you can produce in a regular supernova is around half a solar mass, not that much actually. From 10 to 40 solar mass massive stars, you only produce 0.5 solar mass of carbon, and that amounts to a maximum carbon enrichment, even if you assume the minimum dilution of 6.1. So if you go back to this original plot that I showed about the absolute carbon abundance, you see that it falls way short of the stars, the red circles, group 2 and group 1. It only can explain the lower end of this group 2 stars. So none of these stars, okay? So this cannot be explained. So this is a problem, which means massive stars, which are normal massive stars, cannot produce the carbon that you need, although they can match the carbon to iron, okay? So so we thought of looking at rotating stars. So this was the story that I told you was true for non-rotating stars. For rotating stars, the story is different. So before I go there, here's a model structure of a non-rotating star. X-axis is the interior mass. It's a proxy for the radius. It's easier to plot. Y-axis is the mass fraction, just gives you the abundance. This is a snapshot of when you, just at the end of main sequence, okay? So hydrogen is depleted at the center, helium. So you essentially have a helium core of about 6 solar mass for a massive star of 25 solar mass at the end of the hydrogen burning. So what happens if you take the same model and if it is rotating very fast, what happens is rotation-induced mixing continuously keeps mixing hydrogen into the core, and the core keeps on growing, so much so that by the end of hydrogen burning, you have essentially a helium star. A helium star meaning the mass fraction of helium you can say is almost 1, except for the fact that there is some little hydrogen left in the outer region. So we refer to them as quasi-chemically homogeneous. The word quasi means there is some hydrogen left in the outer regions, but essentially they are helium stars, okay? So you can see that the evolution is completely different, okay? So what happens after helium main sequence? So this is a snapshot of progressively in the later stages of the star, of various stages of helium burning. So I can say that as you can see, the helium burns into carbon. These are the dashed black lines, and this is oxygen. As helium is burning, it will mix out due to rotation-induced mixing, then from nitrogen-14. After a while, the carbon itself will reach the surface. Once it reaches the surface, it can drive line-driven winds. So although a zero metallicity star does not lose mass generally, if metal can get to the surface, it can lose mass. And you can see here, the mass that it will lose is essentially carbon, helium, and oxygen. Here you can see. So this mass that you lose in rotating stars is pure, almost a third of it is carbon, okay? So a lot of carbon is lost, and this is lost in terms of wind. It is not a supernova, it's a wind. So the energies are much less. The typical velocities are 1500 kilometers per second. This is somewhat of a compact star, so velocities are slightly larger. So what we find is, I told you, you produce half a solar mass of carbon in regular non-rotating supernova. You can produce that much just from the wind of rotating stars, just from the wind, okay? What about the rest of the star? So if you keep the wind on one side, you can look at the remaining part, which is the core. Again, the non-rotating star just at the time of collapse. I have just plotted some of the isotopes. And the rotating star at the time of collapse. You can see the black solid line is the carbon here. Very little carbon is produced here in this 25 solar mass non-rotating model, whereas a huge amount of carbon is produced in this rotating model, which is entirely a 25 solar mass, almost a helium star, okay? So what we find here is because they have such a large core, they produce loads of carbon. And the carbon, for example, is about an order of magnitude higher from non-rotating models. For a 25 solar mass, these are the numbers, 2.67 for rotating, 0.27 for non-rotating, as an example. So you have lots of carbon in the core. So now we can ask the question again, what is the carbon enrichment in the early galaxy? So this was what we had for non-rotating star, half a solar mass, 6.1. If you just have the wind, you produce the same amount of carbon almost, but your energies in the wind is much, much less, about 50 times less than a regular supernova. So because you have low energies, your dilutions are less, so you can produce a very high carbon enrichment, okay? And if the star, after ejecting the wind, is able to explode, which is not a guarantee, sometimes they may, sometimes they may not. They can do that. The dilution in this case will be larger, but on the other hand, as I told you, the core has enormous amount of carbon, so that can kind of counteract a little bit, so that you end up with still some A carbon, which is an order of magnitude larger than non-rotating stars. Okay, so this is what we get in the final. So we can explain essentially the entire range of carbon enhancement that we see in the CMP stars. And yeah, so that essentially solves the problem. So we think that rotating stars is the way to go if you want to explain this carbon enrichment, which tells you something about the first stars. So this is the summary of the first part of my talk. The two scenarios can explain the carbon enhancement, and obviously this is telling you the first stars were rapidly rotating. So if the first stars were rapidly rotating, the first second generation star, POP2 stars, the earliest POP2 stars, would likely also be rapidly rotating. What happens in those stars? So they turn out to be doing the same thing that I showed you for POP3 stars, first generation stars, but because they have some inherent metals in them, iron, they produce prolific amounts of what is called heavy elements by S process. So the origin of heavy elements, because of lack of time, I don't have time to go into all the details. It's an important problem in astrophysics. We are still figuring out the details of it. But broadly speaking, this is the solar system abundance, number abundance. You may have seen this many times relative to silicon. This is mass number. You can see that beyond iron, there is a huge drop. These are called heavy elements. These are very difficult to make. The only way to make it is by neutron capture, which is very hard. It comes by very hard in a very limited fashion in the universe. So that's why you have this limited heavy element production. So you can do the neutron capture in two ways. You can start from iron, keep capturing neutrons to produce heavy elements. That's the idea. You can do it in a slow fashion. This will take several 100,000 years, which is the slowest process. And it happens, we think that it happens, at least people think that it happens in AGB stars. There are also observational evidences. So the important thing to note here is because they are low mass stars, they cannot operate in the early galaxy. So S process per se should not operate in the early galaxy because of the long lifetimes of low mass stars till they get to AGB phase, right? The other way is rapid neutron capture process. So instead of 100,000 year time scale here, you do this in 1 second, 2 seconds, maximum 10 seconds time scale. So you have lots of neutrons for a short amount of time. That happens in neutron star mergers or magnetorotational supernova. So this can happen in early galaxy, and they're prolific, but the thing is they're rare. They're rare. Okay? They produce a lot, but they don't happen very often. But they can operate in the early galaxy. So they expect that the early galaxy is mostly R process. And observationally speaking, without going into the detail, you can differentiate between the output, the nucleosynthesis output of the two processes by just plotting the abundance pattern. This is the elemental abundance pattern in terms of atomic number. And I've normalized it to barium. So you see the red curve, red dotted curve is R process, the blue dotted curve is S process. They're different, of course. You can see different peak positions, but if you want to measure just two elements to see which process is this, you can measure barium and europium. Here is barium, here is europium. You can see barium and europium is around 10. Number ratio is 10 for R process. This is about a factor of 2,000 or more for S process. Okay? So they are clearly different. And now, so people expect R process to operate in the early galaxy, no S process. And then there is some other process in between, which is called intermediate neutron capture process. The site of this is still uncertain, but the idea is this is neither too rapid nor too slow, somewhere in between. And they lead to abundance pattern that lies between this red and blue curve, okay? And they are sometimes referred to as R/S pattern, okay? So there are some major unresolved problems. Unfortunately, I don't have time to go over them, but I'll just list. So one of the things is this S process should not exist in the early universe. But I told you the CMP S stars that I showed you earlier, they're thought to be in binaries. But there are some hints that some of these are single stars. So if there are single stars, then you need to explain the S process in these elements, in these stars. Now they have also found stars that look like R/S, something in between R and S among the CMP stars. So then origin of I process, as I told you, is uncertain. We don't know the exact site. There are some suggestions. And then, as I told you, you can measure barium and europium in many, many stars. And barium and europium gives you an idea whether it is R process or S process. So what we see is the barium and europium starts out as R process in the early galaxy, but quickly tries to go away from that value closer to S process. So this early onset in the very early galaxy of S process is something which people don't understand. And lastly, what is interesting is that whenever you can measure heavy elements in any of these very metal poor stars, it's above the threshold, detection threshold, you always end up measuring strontium and barium in these very metal poor stars, which means in the early galaxy, this heavy element production must have been very, very common. So you cannot explain that with rare R-process sites like neutron star mergers, okay? So all this points towards some additional neutron capture mechanism in massive stars, including the first massive stars. So the idea is that massive stars are by far the most common nucleosynthetic source, and you should expect that if they can produce heavy elements, then you can explain the ubiquity of heavy elements, and if they can produce S-process patterns that can also I-process patterns, you can address these two as well as the fact that you see a deviation from S-process values, R-process values very early in the galaxy, okay? So as I told you, the rotating stars that I showed you for first generation stars, if you just repeat the calculation for stars which have some inbuilt metals in them, meaning from their birth material, iron. So they have, let's say they have iron 1,000 times less than the sun, FE over H of -3, and they happen to be a massive rotating star. They can produce lots of neutrons. So how do you produce neutrons in stars? So the mechanism is very common, very simple and commonly known. What you need is three resources: hydrogen, helium, carbon-12, and hydrogen, protons. And you need temperatures where it is at least hot enough, which means 10 to the 8 in this case, okay? So the reaction chain involves the first two reactions in the CNO cycle, so which is known to everyone. You do proton capture on carbon-12, nitrogen-13. Nitrogen-13 will beta decay to carbon-13 in 10 minutes, and then you can release. This is the last step, is the most important step. This happens very commonly in nature. The last step is very uncommon in nature, which is you can get the neutrons from a carbon-13 back if you have helium and if it is hot enough, 10 to the 8. So you need this condition, which turns out to be extremely rare in the universe. Almost, I mean, it's only found in very, very specific cases. As I told you, AGB star is one case. Okay, so this is what it is. You need helium burning products mixed with protons where the temperature is hot enough. So this is exactly what happens in rotating stars. So this is a plot again during hydrogen burning, during helium burning. The green line is the helium. What I've done here is I have this dashed line is carbon-13. So what I've done is I've enhanced the abundance of carbon-13 by a factor of 10 to the 3 so that you can see clearly. So you can see that here in this region where carbon is leaking out, they produce carbon-13 by CNO cycle by reacting with a little bit of protons. And what happens is this carbon-13 then can mix back into the core as the core goes convectively, and then this carbon-13 alpha N will produce neutrons. So this is the neutron abundance on the red solid line. As you can see, it's highest at the center because it is hottest at the center, okay? So this, it turns out, gives you prolific S-process so you can produce lots of neutrons, and what is happening here is you have iron sitting in the core that will see these neutrons, keep absorbing these neutrons, and how long do you have? You will have all the time when it burns helium. So it's a long process, 100,000 years, you can easily do that. This is exactly the time scale for S process. And in the innermost region, the neutron abundance can be even high as close approaching I process. That is what we found, okay. So what happens? S process will happen here, some of it will be mixed out, lost in the wind, some of it will be in the core, which can be ejected if there are explosions. So due to lack of time, I'll just show you the results. So on the left, what you have is a CMP S star, which is a star which looks like S process, okay? And on the right is a star which is one of the well-known star which looks like a mixture of RS process. So what we found is if you just have the wind ejecta going into the ISM, you can exactly explain the S process very well. So you can explain all the things from strontium, so this is atomic number, strontium, here is barium, here is lead. Lead is where you sort of finish your neutron capture roughly. So you can explain everything very well and the pattern matches very well. And if you are able to eject a part of the core which have these higher neutron densities, you can actually also explain quite well the abundance of RS stars. So we did this for many CMPS stars and found that you can explain the abundances of many of the CMPS stars and even some of the RS stars. Not all, but some, okay. So that is the summary of the second part. So the same thing that we did in POP3 stars, which gave us carbon, gives us heavy elements plus carbon in POP2 stars. And they obviously will be very common in the early galaxy if the first stars or early massive stars were rapidly rotating. And they can give excellent match to observations, and then can also, as I told you, solve the problem of heavy element in general in the early galaxy. Okay. So one of the things I did not show explicitly due to lack of time is that if you repeat the calculation at different metallicities, this automatically turns off, which is a very nice feature at Fe over H of minus 1.5, metallicity of minus 1.5, it automatically turns off due to high mass loss. The rotation mixing is not very efficient due to higher mass loss at higher metallicity. So this is a feature that only comes in the early galaxy. And this is also consistent with the fact that most of CMP-S and RS stars are also found in the early galaxy at low metallicities. Okay? Yeah, so with that, and the final thing is you can put the two together and see that there's a common origin between the CMP no stars, and then some of the CMP-S and RS stars, and both of them suggest that the first and the early massive stars were rapidly rotating, and that will have very important implications in our understanding of the nature of the first stars. Thanks.
Thank you, Prajwal, for this interesting talk. So we have time for many questions. So please go ahead there first.
So, Prajwal, I had a naive idea that the rotation of stars is directly related to its age. That is, that it slows down as it ages. Is that, not a factor here?
So these are born with very high angular momentum. So it may slow down if it loses, it quote unquote slows down if it loses mass. But as I told you, by the time main sequence ends, it is already the helium core has already formed, like chemically homogeneous, and there is sufficient rotation after that to sustain rotation mixing, where you can mix carbon out a little bit. So all of that we don't see. I mean, there is slowing down. We have magnetic braking in our calculation, but it's not enough to slow down completely. It does slow down though, yeah.
Okay, thank you.
Yeah, we go there. Next question.
So about the first part of the talk only. So you said POP3 and POP2 both can have very high rotation to start with, but the environment from the start is can be different, right? Because one is out of cloud, the POP2, and then you have metallicity more, and the other one is different. So
that is true. Yeah, I mean there are arguments, but I am talking about very early massive stars, meaning a metallicity of -4, -3. So that can happen literally even in relatively small halos, where I mean the cloud star formation could be this transitioning from low, high top heavy to salpeter-like. So yeah, I mean there is no strong argument that they must have rotation, but there are some suggestions that if you go to LMC and SMC, you do see more rapidly rotating stars than in our local galaxy. So that idea you can extend to very early galaxies, saying that in any case, if you go to 100 times or 1,000 times less iron, rotations would be rapid. Whether they'll be extremely rapid, that we don't know.
A nice talk, Prajwal. So this about this CMP-S stars, like we know that most of them are in binaries, and so do you think this this channel, whatever you are proposing, does it operate in very specific metallicities compared to the other AGV binary mass transfer?
Yeah, essentially it operates at exactly the same metallicity as you see the CMP-S stars, -2, -3, in that range, -3 to -2 Fe over H. So, so there is that's not different from the AGB star. I mean, AGB stars operate at all metallicities.
Correct.
This operates at -3 to -2, where you see the CMP-S
so
stars.
would you be able to say that this channel dominates in certain metallicities compared to AGBs? Or,
yeah, I mean, we think that it should be quite dominant, but the only thing is the binary companion, we have some constraint on the nature of binary. Sometimes you think we know that it is a white dwarf. In this case, if it's a binary, then it has to be a massive star with a low mass star companion. That I don't know how likely it is, but it can happen because these are winds. Winds are slow, so there can be mass transfer to binary companions. In regardless, so there are some CMPS stars which are not in a binary, at least we think, may not be in a binary. So then this becomes the only way to kind of do this. And also it can just do S process in the early galaxy anyway, as like a chemical evolution, rather than mass transfer.
Yeah, one more question there.
Hi, thanks for the nice talk. Am I correct to assume that you are considering mixing and rotation in a spherically symmetric model?
Yes.
And then here's the blunt question: how trustworthy is it? Is the mixing and chemical instability, fluid instability is properly studied in such a system to assume it to be properly
Right.
representing?
Yeah. The short answer is it's not reliable in that sense that we have not studied it. The way it is done is, yeah, we approximate the mixing and put it in a 1D format. The mixing due to, let's say, meridional circulation and shear mixing. There are some, so what has done is that we can do this for LMC, SMC rotations, massive stars, and match the nitrogen abundances. So the way we do this is there are mixing and there are some parameters that control the efficiency of mixing. It's matched to match the nitrogen abundances of rotating stars, and then we use the same parameters for low mass stars, low metallicity stars, and get this evolution. So in that regard, yeah, that is some kind of calibration, but no first principle calculation.
I see. Thank you.
Yeah, we have a last question.
Prajwal, very interesting talk.
Thanks.
When you talk about this rotation and all, you tell nitrogen is coming up, S process elements are coming up. You also mentioned helium is also a very important ingredient. What about helium? Does it also get enhanced in this process?
Yeah, I mean, essentially you convert the entire star into a helium star.
Yes, yes.
So helium is the most enhanced in some sense, but in the wind also you lose a chunk of helium. So in the wind, 1/3 is helium, 1/3 is carbon, and 1/3 is oxygen. If you transfer that material to some low mass star, then it could appear to be like a considerably helium enriched.
So has any studies done to look for helium in such stars?
No, I don't think so. But it is an interesting thing because this mass that will be transferred, could be transferred, would be quite helium rich.
Thank you.
Okay, yeah, we have to go on. So thank you, Prajwal, again. So yeah, the next talk, you can go ahead. Yeah, next talk is by Arkaprabha Saragi, Supernova and the Origin of Cosmic Dust.
This is good. So it is of great pride and pleasure to speak at this General Assembly, and I would like to believe that people at the very far corners of this auditorium will remain interested in what I am going to say. So I want to connect cosmic dust and supernovae with various aspects of astrophysics. Naively looking at any galaxy, we find stars. They hold almost all the mass of the baryonic universe, while on the other hand they are so compact that they only occupy a very little volume of the galaxies. On the other hand, the rest of the galaxies we see are full of molecules and dust grains, which are basically chemical compounds made up of few tens to hundreds to thousands of elements together clustering, and that is what you see. So if any cross section of the observable universe you go to, you will find tons and tons of these clusters all around us. But that would mean that we would have at some point of the universe have gone through several phases of chemical reactions. So where we can have these chemical reactions? to look for that, we go to all the places in the universe and then we go to stars. We find that the stars are too hot and they do not provide us conditions where we can have neutral molecules to have formed inside the surface of the star or even inside it at all. If we go to the interstellar medium is cold and diffuse, and if I give you a ton of elements, most of the elements to grow to molecules and clusters would need some coffee to go through these phases, and they do not have that energy to go through. So what happens is that we do not reach conditions to go through chemical reactions in the interstellar medium starting from elements. We are left with the environments of evolved stars. What are evolved stars? Which are stars in the end of their lives, which has gone past main sequence. In this figure in HR diagram, you can see all these stars from the left end to the right end which has gone past its main sequence. They provide conditions which have accurate physical conditions such as high temperatures but not high enough to ionize everything. On the other hand, also have very high densities. On the other hand, these conditions only are, say, in a galaxy there is 0.5% of the stars at a time which are evolved, and also they are very, very short lived, which means that whatever I will be talking about happens in a very rapidly like evolving phase and out of equilibrium, unsteady conditions, and all these galaxies around you, what you see, the molecules, clusters have been produced, at least the seeds of them have been produced in such conditions which are very, very rapidly evolving and turbulent in many ways. In this talk, I will focus on the evolved stars from massive stars, evolved massive stars which are above 10 in solar mass, and I will talk particularly about the red supergiants, the supernovae, and the ultra-H stars. Now, why do we want to talk about supernovae? If we go to the very earliest galaxies, which are less than 1 billion years old, we see a lot of dust present in those galaxies as well. And only massive stars which live only a very few million, only live a few million years, they have that time to reach to that evolved condition to have produced those dust, while low mass stars would not have reached conditions that could produce dust in those stars. So supernovae gets a major push from the early universe that they should be one of the major drivers of forming molecules and dust in the early universe. This can be seen in our local universe as well. If we look at supernovae around us, like supernova 87A has notoriously been very, very dusty from the very origin, and if you see the evolution of it from its commencement to now, and with the JWST image taken 1 year back, they find a lot of dust present in the inner core. This is the ejecta and this is the ring. So in the ejecta itself, they find a lot of dust present inside. You can even find it on Earth. If you take a meteorite sample and if you make a cross section like the one that I am holding, you can see grains inside which have the elemental abundances which matches the nucleosynthesis phases that Prajwal was just talking about. So they do prove that supernovae has produced dust grains which have been transformed to us, which has been carried to us and which we actually have on Earth or on the surface of the moon. Now, massive stars become important because a lot of these elements that we see embedded in molecules and dust have actually formed in those ones. Like if you see the periodic table and their origin, you see the oxygen, neon and magnesium and part of silicon and part of carbon, they all come from exploding massive stars, and the lot of these elements are actually found locked up in molecules and dust grains. Now, how do they actually form? I am talking about we need a lot of chemical reactions, right? So because the environments that we see around us are so turbulent, we can only form them in a very non-equilibrium kind of way. To model that, what we try to do is we take into account all possible chemical reactions and then we grow them through phase by phase. Initially everything remains ionized and then they become larger and larger. They form neutral molecules and molecules grow to clusters, they grow to nanometer sizes and then they grow to even bigger, close to 0.1 to 1 micron, which we actually see in the interstellar medium. And that goes through nucleation and coagulation and accretion, and all these phases happen in a coupled together. So gas phase and dust phase gets coupled because some molecules molecular reactions while are already occurring in the gas phase. On the other hand, you already start forming some dust grains in the gas, and computationally you have to take into account all of them together because you don't know which interplays with each other. Now back to what I was. So this is the mechanism of how you form. Now I will be talking about the massive stars, as I said. So if we look at the red supergiants, this is a zoomed in HR diagram. It is the same diagram that I showed. If you look at the population of stars in the Large Magellanic Cloud, there are a lot of red supergiants as you see in the far end. They are relatively cool stars which has temperatures between 2000 to around 4000, and their luminosities are between 10 to the 4 to 10 to the 5. Now observing them, we have a lot of them in around us as well, like Betelgeuse and Antares. You can actually see them, VYCMA, you can actually see them in our night sky. If we try to observe them, what we will find interesting is that a lot of these stars show evidence of high mass loss in the very end phase of their life. This figure on the left, what it is showing is that after those evolved star, red supergiant has exploded as a supernovae, it has shown signs of very dense material present around it. Two interesting things to look at this figure. One is that they have found a mass loss rate of 10 to the minus 4 to minus 3 per year looking at the X-ray luminosities, and secondly the interaction with the X-rays are found immediately after the explosion. These are 10 days or even before 10 days, which means that whatever mass loss has happened in that star is sitting right over the star, which is unusual because stellar wind is common. We all know stars are bright, they can drive away wind. But these are cool stars, and also these winds are not being driven away, they are almost sitting on top of the star. So this mechanism remains unknown. We do not actually know what can drive such mass loss phases where mass loss is high but the velocities are low and they just sit around the star. These mass loss winds or whatever these circumstellar material, they actually sit around the star and they are a place where you can form a lot of dust. Lately there has been a lot of observations of supernova progenitors, like you see 2025 PHT, which has bright infrared emission detected by JWST. And so what I want to say is that they have a dense circumstellar material, and this circumstellar material is dusty in nature. So both are open questions. How do they form this circumstellar material? How is the mass loss rate so high? And also, how do the dust form in that wind? To look at that, we actually try to simulate these massive stars, and lot of them, these red supergiants, because they are so large in size, they tend to pulsate in the very end phase of their life, which is very difficult to show in a PDF presentation. But the way that they pulsate, sometimes they reaches L by M conditions, the luminosity to mass conditions, that creates phases of enhanced mass loss. This enhanced mass loss can be parameterized mathematically to have phases of mass loss which can reach 10 to the minus 3, minus 4, which is not normal for stars like this. And so we simulate conditions which would lead to super wind kind of heavy mass loss, and then another phase called dynamical ejection, which is a kind of eruptive mass loss. When there is a buildup of shock on the surface, then this mass gets ejected suddenly out of the star. These are motivated by observations because there are a lot of supernova progenitors which has been measured for the column densities, and we try to match what type of column densities we can have, and also we could actually get an idea about the progenitor mass, because different progenitors 12, 13, 14, 16 as I am showing, they all evolve differently. So based on the progenitor mass, how these winds will be produced and how this dense CSM will be around the star and how much column density of gas you expect, these can be matched with the supernova progenitors to find out what type of mass the progenitor did have. Now, this is the gas. We have produced some circumstellar material around it. So this is a cartoon of showing how this mass loss happens. So this is the red supergiant. It has driven some winds. Winds can have different velocities. I will not go into the details of that. It can be a continuous wind. It can be accelerated after it is ejected. And then when suitable conditions appear, you start forming some molecules, then those molecules grow into clusters and those clusters grow into dust. And if they are produced very close to the star, it will significantly impact the spectra of the star, because the light from the star will pass through all of that and the infrared emission will be completely dominated by the material around it, infrared and optical both. And that is what is I am showing here, based on just theoretical estimates of different mass loss rate, what kind of spectra you get, and we compared it to the circumstellar spectra of, spectra of the progenitor of 2023 IXF, which has HST and Spitzer observations, and we tried to see what kind of temperature of the star would fit well with the, and the mass loss rates would fit well with the observed spectra when we produce dust in those winds. And also we found that there is a significant evidence of these winds being clumpy in nature, which is both found when we are matching the column densities as well as when we were doing the spectral modeling after the dust has formed. So this is also observationally often proposed, that these winds from the stars are not entirely smooth but in clumps, and our models also have found evidence of that. Now, I will also talk about ultra-H stars, because whatever I was talking about red supergiants exactly get flipped when we look at the ultra-H stars. If you see these very end, ultra-H stars are extremely luminous and more importantly has a very high temperature. So it can drive winds very fast, and it provides you conditions, everything that could never be able to form dust, because it has a very fast wind, mass loss rates are very low and the temperatures are very high. So how will you have chemical reactions over there? But there are evidence of lot of ultra-H stars around it which are dusty, like ultra-H 140, which has been observed in several telescopes lately with JWST. And what we have found, that there is a special scenario where these binary ultra-H stars have a colliding wind between the two, and then due to this collision, I am just showing for ultra-H 140, which has a very eccentric orbit, has a eccentricity of 0.89, and because of this eccentricity, when they are very close by, due to the collision, you have high densities and that drives shocks, and shock leads to radiative cooling, radiative shocks leads to radiative cooling, and you form a very dense shell. With all this history I am not showing, I am just showing the result, that when these stars are very close in the phase, you have this small region where you actually form dust. On the other side you cannot, because then the winds are not as dense enough when the stars are far out. And that leads to this ring-like dusty shells, and this is theoretical, like how these dusty cells propagate. We do not exactly match how this looks like, but this is the idea of how these dusty rings will propagate when you have colliding winds in binaries. If it had been a single star, I have not known a theory which would be able to produce dust in the wind of a single ultra-H star, because of this high temperature and low mass loss rates and high velocities. Now, I am supposed to talk about supernovae. 20 minutes gone, I have not yet reached there. So all these things happen just before the star explodes. Now the star has exploded, and now there can be different phases, because I was talking about mass loss rate, right? Based on mass loss rate, the star can lose a lot of its hydrogen shell, the star can lose a part of it, depend on that how the star will look at the time of explosion. Now the star explodes. This is a complex picture, but I will like to break it down. It is complex in reality. Everything gets exploded in a very rapidly evolving manner. So whatever star was doing for millions of years, in a blink of an eye, it gives all the material back now in the interstellar medium, going towards the interstellar medium. And we have a lot of radioactive species. Radioactive species control the temperature, and these nickel-56 control the evolution of what is happening chemically in the gas. And all this expanding gas has this race against time, that if you get suitable condition, it will lead to dust formation. If it does not, then the gas will just become too diffuse and you cannot. And this is clearly seen in supernovae. Some supernovae end up producing a lot of dust, some do not. Just because of how you explode, how much nickel you produce, what is the explosion energy, how much fast the velocity it is, and how fast it is expanding, based on all these factors. Now, to simplify the picture back, this onion shell-like structure it had before the explosion, it kind of retains the structure, especially in 1D model. You can assume that because it is not easy to assume mixing in there, and we have found evidence in observation that there is no microscopic mixing between these layers, means you cannot take one layer and mix totally with the other one. There can be some surface mixing all the time, but those are macroscopic in nature. That does not affect the chemistry, because chemistry happens in microscopic scales. So if you look at these zones, you see there are some carbon rich zone, there are some oxygen rich zone, and the chemistry will be different in each zones, and you will end up forming multiple type of dust grains in a supernova in this metal rich core of the star. In the same chemistry that I was talking about, I will not repeat it, but all these reactions happens in those environment based on what elements you have in what regions, and you end up forming different dust masses. So this is a summary of what kind of dust, how much of it you expect from different progenitor masses. You see there is a large dependence on the progenitor mass on type of dust. You see carbon dust becomes important for smaller progenitors 10, 12, and then it decreases. Oxygen rich dust keeps on increasing. There are some aluminum rich dust and silicon carbide dust as well, but mostly silicates and carbon dominates the supernova dust that comes from it based on the progenitor. Also you see there is a large amount of stochasticity in the results, and when we go deeper into the stellar evolution to compare that, we actually see that there is a large amount of randomness also in the amount of nickel and silicon you produce, actually magnesium and silicon you produce in these massive stars, and it is a matter of research on what is the reason behind this large amount of randomness. There are some theories on mixing in the boundaries and also several mergers between the shells that increases the abundance of one species versus another. There are other species that also shows this randomness, but because silicon and magnesium goes directly to form silicate dust, and silicate dust forms shows this large amount of stochasticity, I am showing how much random the abundances are. If you see this 18 and you see 18.5, you see there is 2 order of magnitude difference in how much silicon a star has produced. And this remains a matter of research both theoretically and observationally, that how can we constrain the amount of heavy elements a star is producing. All these were theory. Now we have to actually account for that in observations as well. So how much do we actually find in the supernova around us? These are the summary of all supernovae that we have observed over the few decades, and you see that there is a certain amount of gap. So there are 2 things here. One is that you see the masses over here is of the order of 10 to the minus 4 solar masses in the first 1000 days, and then there are 2 supernovae remnants observed in late times, which has observed very high masses like close to 1 solar masses. And there is a large gap in observation in this period because the supernova remnant became too cold to actually keep tracking in the infrared. Now this leads to this supernova dust mass problem, where theoretical models have predicted that supernova is a very suitable place to form dust. It will produce a lot of it within the first couple of years, which observers have not been able to find, and there are debates on is it that we miss the dust, or is it that the theoretical predictions are not accurate? Is it too optically thick? Is the light actually coming to us, or we miss a large part of it because it becomes cold? All these theories are present. Last 2 years we have been able to shed a bit of infrared light onto this because we have JWST data now coming. We have a lot of active programs going on, and we are detecting supernovae around us, which is 1 minute I will take that this is really amazing to think that these objects, some of them are 20-30-year-old, it does not have a star, and it is just a cold expanding gas, and yet it is bright enough that we can detect them after 20-30 years with an infrared telescope. The first detection happened of 2004 ET, it was in a lot of news, and then we have been able to detect around 17 to 18 supernovae until now, and I will just show snippets of 2-3 interesting results. You see this is 2005 IP, This supernovae was one of the brightest interacting supernovae with a lot of circumstellar material around it, and it was detected after 18 years. It was the first supernovae which showed PAH features. You see these clear PAH lines which has never been observed before in any other supernovae. This is the infrared spectra, and these peaks you see, this belongs to the silicate nature. These two bumps, one at 10 micron, around 10 micron, and one around 18 micron. If you go to the another object 2007 IT, which is the current one, this is not yet published, we are finding that a very large mass, close to 0.2 solar masses of dust, dominated by carbon rich components. No other supernova has been detected with this level of dust, warm dust in there. In supernova 87A, people have found 0.4 to 0.6, but that is cold dust. So there can be some contamination here and there, but in this case, this is warm dust coming from the ejecta itself, and 0.2 is not yet published, but it should be the largest among the normal core collapse supernovae that has been detected until now. And then coming to the summary, all these supernovae we put together, if you look at what I was pointing out, 2007 OD and 2007 IT, which are the current two supernovae we are working on, the JWST results, you see there is 3 order of magnitude difference in the dust masses. So all these theoretical, all these idea that supernovae explodes, it has heavy metals, it will condense, it will produce dust. How does this randomness happen? How is it possible that two supernovae, both 20 years old, has 3 order of magnitude difference? All were massive stars, they were all between 10 to 20 solar masses of progenitor, and they should not have these large difference unless there was something happening in the star, how they evolved, that have been captured in this detection. The same thing happens in the luminosities as well. There is a large spread in infrared luminosities, while type 2Ns, the interacting supernovae, are found to be more luminous, which is expected. Another interesting aspect I will end with is that the light curves of supernovae remains bright for decades after decades, which is still a mystery. We do not understand exactly how, because to have something in the infrared, you need an optical source. These guys do not have an optical source. There is no star there, there is nothing there, and until now we thought that they would just become a cold expanding gas, but they are found to have bright infrared luminosity even after 2-3 decades post explosion. And who is heating these guys up after 20? We have tried to find optical sources. We have put HST, we have put EC to all these objects, but there is nothing in optical. There is no signal coming in other wavelengths. On the other hand, infrared is still bright, so it remains a mystery why they have such a bright infrared light curves after such a late time. So I like to finish here thanking all the people working with me at IIA, and they have contributed to a lot of this work that I was presenting at. The summary is that as I said, massive stars lose mass. It remains an open question how, especially red supergiants, what is the mechanism for them to lose mass. These randomness of the elements, we have to connect stars with the dust to actually find out the history of stellar evolution, because it is only in dust that you are able to see what was happening inside these stars for millions of years. So once you understand what is present in dust, you would be able to tell what happened in the star during its lifetime. And finally, these massive stars produce a lot of dust and we are detecting them now, but are they enough to account for the early universe, how the large amount of dust there? That remains still a question, and we need better theoretical models and more data in observations to build this hypothesis strongly. Lastly, there is an advertisement. I am happy to say that we will be organizing IAU Symposium next year. The topic is Dusty Stellar Environments Shaped by Winds, Eruptions and Explosions. It has been approved only last week, and I am the SOC chair. There are several chairs, but I am one of them, and we will be organizing it, proposed to organize it in Goa, and I would like to see many of you present there. It will be a nice discussion on how stars evolve and how they form dust. Thank you.
Thank you, Arkaprabha. So we have time for questions. Please raise your hand. Yeah, there.
Hi, very interesting talk. I have one question regarding the environment of the supergiant and the red supergiant and the wolf rayet stars. So you are mentioning that there are dust grains. So are there any studies on the size of these dust grains around these massive stars?
So there is like when you are fitting a spectra, you would need to assume some kind of size distribution, but we have seen that it does not have a significant impact on the spectral result. So it would need, whenever you have some data to match it, you need to have some kind of size distribution of the grains. Theoretically, we do like when you are forming these dust grains, we have to produce them by distribution of sizes. So we have that theoretical estimate. It does not impact too much into the spectra.
Okay, thank you.
So this is regarding the plot that you showed that there is a 3 orders of magnitude difference in the dust masses for similar supernovae, and you said this must be attributed to a difference in the properties of the originating star. So, but given that these supernovae themselves are quite similar to each other, they're all coming from the same kind of massive stars, why is there such a large variation in the dust mass?
Yeah, so their progenitors are all between 10 to 20, and only the progenitor mass would not be enough to explain this discrepancy, that I agree. But there can be other aspects like the explosion energy and mass loss rates and all these things, and the stochasticity in how much elements are produced, those can impact largely, but how much, it's still open.
Are models and simulations able to predict this difference, or?
Yeah, so see, if I take say thermonuclear supernovae, which are very very fast evolving, we would see very easily that we would struggle to produce any dust there. So all these ranges are there, but say we can have supernovae with very high energy, very little ejecta mass, which would end up forming no dust at all. But what kind of condition was there, that is still unknown.
Yeah, very nice talk, Arkaprabha. So I have just a naive question. You mentioned that dust can only form if you have a colliding wind binary scenario in WR stars. But what about there are studies where they have shown wind clumping and episodic mass loss, right? And that could also so is it correct to say that you will have only if you have colliding wind scenario?
So theoretically speaking, I think in those cases there has to be colliding wind of the own star that leads to formation of the dust in single ultra stars, because the mass loss rates are too low and the wind is too fast to actually form these in a just free flowing gas. So you need some kind of enhancement that happens when you have collision between the own wind as well as like binary stars hitting each other.
Because there are some cases like I think WR7 or something, it's a single star, but you do see dust formation.
Yeah, so that can happen. One of the scenarios I proposed that can have like different phase mass loss which are building up against each other. But yeah, other theories are still unclear. I also don't know.
Okay, thanks.
Yeah, thank you again, and we'll go to the next speaker.
Thank you.
Thank you. Anshu is next speaker is Anshu Kumari. She will give a talk on solar radio physics from instrumentation to observations.
Good morning, everyone. I am Anshu. I joined PRL slightly over 1.5 years back, thanks to the for having me here to discuss about my work which we are doing at Udaipur Solar Observatory of PRL. I will be discussing about the instrument we are currently developing and some of the science results. So you have seen the sun in multi-wavelength multiple times in extreme ultraviolet, X-ray, or say white light images. This is how the sun looks like in radio wavelengths. So you can see there is the background sun which comes from a thermal emission, and then there are these blobs which comes from non-thermal emission, and there are three components in the solar radio observations which we do. The one from the quiet sun, the background, the one from the active sun, and then from the eruptive sun. And these are most important when we talk about space weather aspects. So if you look here carefully, there is frequency here which increases from 300 megahertz to 17 gigahertz. This image is slightly old and made up with 3 different instruments across the globe, and you can see the brightest source temperature shown here. So it first increases and then decreases, and so that would correspond to mostly here. So if one can say that sun appears to be like a fuzzy blob in radio wavelengths. So why do we care about the sun, especially in these wavelengths, when if you see we have a very poor spatial resolution? So hold on to that thought. In a standard CME flare model, so basically the solar transient model, we have the photosphere, and then magnetic field lines are arced in the photosphere here, and then we have the magnetic field loop here. And when anything that happens on the sun, so any transient, when it moves outwards, it will compress the plasma above it, and then we see this shock, this solid black line. And all the numbers which are written in this 2, 3, and 4 in Roman letters are Roman numbers are the signatures of this particular transients which is happening in the sun in radio wavelengths. So basically, one can see that each and every part, some emission can also come from here, each and every part of this transient can give some signatures in radio wavelengths. For example, this is the shock which is moving ahead, so we have a signature of called type 2 radio bursts in the solar dynamic spectra as well as the images. Then along the open magnetic field lines we see a type 3 radio burst. It tells us how the electrons are accelerated and how it is transported. And then from the foot point, and also in very rare cases from the core of this coronal mass ejection, we can see a type 4 radio burst, can come from post-arcade loop as well as the core of the CME, and at present from observational evidence, this is the only way to estimate the coronal magnetic field in the middle corona directly from the data or observations. So one can say that each and every part of the transient has some signatures in radio wavelengths. And what are these eruptions are basically the signatures of accelerated electrons in the solar atmosphere. So for example, if you see 300 megahertz would correspond to slightly higher heights in the corona, and 17 gigahertz would corresponds to lowest corona and uppermost chromosphere. So this means as one moves out in the solar atmosphere, the plasma frequency decreases. Again, magnetic field also mostly decreases, depends upon the time of the observations. And so if we are tracing this, basically we are tracing layer by layer information on the sun, and that is what we try to do in radio observations. Since these are the direct signatures of accelerated electrons, we can also, because we are tracing the heights, we can also trace how it is moving in the solar atmosphere. So this is one of the only wavelength that can give us these kind of information. So coming to how do we do all these observations there are 4 types of observational technique. The first one is single frequency observation. Some of you have heard about f10.7 centimeter or 2.8 gigahertz observation, which is the second most reliable method to predict the solar variability and cycle because it is the longest, one of the longest available data after sunspot cycle. So this is the current scenario. This is a global picture, how it looks like, what kind of instruments we have for these kind of observations. So x-axis is time and y-axis is frequency. It appears quite filled. However, 2.7 centimeter, 2.7 gigahertz, we only have 2 instruments currently operational in the world, and none of them are in Asian time domain. This is how the observation, this is sun as a star observation. So this is how the data looks like when we do the observations, and then we calibrate and can also get polarimetric information. The second type of observation is a spectrometer and spectropolarimeter. This is again sun as a star observations, but we get more information because we have a continuous coverage in frequency. That means we are continuously tracing or tracking the solar layers, solar atmosphere layers. So this appears that this is quite filled. We have a lot of instruments in the world dedicated for solar radio spectrometer. However, note that there are none for spectropolarimeter. This is how sun as a star observations would look like. So the background is quite sun. The bright features here are the emissions associated with different kind of solar transients. Then the third observation, when we resolve the sun, we can do solar imaging using interferometric observations, and that's what we have done here. So again, we have time and frequency. This light brown color instrument is not operational here yet. It's just this is for all the instruments which were operational, are currently operational, and will be operational in future. So this scenario, if we just remove this, looks like almost at low frequencies we have IIA's Gauri-Badno Radio Observatory's graph instrument, and then at high frequencies we had this instrument in Japan which is not currently operational, and that is why we have currently are going to develop this particular instrument Arun at Udaipur Solar Observatory. So if you see here at different frequencies, when in EUV observations you could see some brightness and some waves moving, and each and every part of wave has a counterpart in radio imaging observations. And imaging is important to pinpoint the location of the accelerated electrons in turn where the transient was happening. The last kind of observation is called direction finding observation. This is done with space-based instrument because we cannot put a interferometry instrument in the space. So we use multiple spacecrafts. So and then we can trace how this is the tracing of different layers on the sun is what I was talking about. So you could see electrons which are accelerated and how it is moving outwards from the sun. So this is especially for great importance for space weather purposes. So radio observations alone are not sufficient. We always combine it with multi-wavelength observations in white light, X-ray and EUV. So in this plot here on x-axis we have frequency, on y-axis we have height above the solar atmosphere in terms of R0 and kilometers. So these three lines tells us three different kind of emission mechanism which are expected from the sun in radio wavelengths. So plasma emission, bremsstrahlung and gyroresonance and synchrotron. So just by looking at your observational frequency we can tell what was the emission mechanism, and in turn we can also estimate heights as it can be seen here. This is again model dependent, but most of the time it works, and we can also estimate coronal temperature as well as the plasma conditions. When we compare this with multi-wavelength observations, these two images are from Aditya's VLC and suit. This lower portion is covered by X-ray, EUV, and slightly upper portion of the corona is covered by coronagraphs. This is just an example. We have multiple other spacecrafts dedicated for solar studies which can give us information in this region. But these regions also have counterparts in radio techniques. So lower frequency, lower heights, that means the higher frequencies we can do ground-based radio interferometric observations. So this image is taken with GMRT. And then for say higher heights in the heliosphere, we use a technique called IPS, for which UTI, this image is taken from UTI. Yesterday some of you have heard the talk by KK where this telescope has started observing IPS regular observations again for the past 1 year. And in between we have Faraday rotation methods. Though it is very well established, how it has not been very well probed for solar studies, but this can give us magnetic field variability, especially in these height ranges. So it can also be done from a spacecraft signal and coming to the earth, or from a, say, a pulsar signal coming to the earth with observed with some giant radio telescope. So if you see above 10 megahertz, we can do ground-based observations. We do have multiple instruments, as we have been seeing. Below 10 megahertz we cannot do because ionosphere would not let radio waves come down, so we have to go to the space. India has a lot of instruments definitely not dedicated to solar radio case, but we have radio instruments at GMRT and at OT to do, we can do this solar studies or heliospheric studies, and we also have a dedicated imaging instrument at Gauribandhu Radio Observatory for the lower part, this imaging part. However, India does not have any radio payload till now. Aditya has multiple wavelength observations instrument as shown here. So to complement this, we are building some radio instruments at Udaipur Solar Observatory of a PRL. So this is the team. Most of them work in instrumentation and some of them work in simulation. So I will not be covering simulation part in this talk. So this is how the radio environment at USO looks like. So this is from a few megahertz to 2.5 gigahertz. So you could see a lot of bands, but if we just zoom in, we have a lot of usable band. Again, sun is noise for other people, it's RFI for other radio astronomers, it's the main source for us. So when the sun is active, we can also see the signal going much above this in some of the cases. Usually we filter out the frequencies we do not need using notch filters. So this was maybe 6 years back, USO had established a ready-made system. It is called eCallisto. This is a couple of these instruments are in India and a lot of are in abroad as well for 24/7 monitoring of the sun. So the front end is a log periodic dipole antenna and the back end is this system in a board which can work from 40 to 400 megahertz. So building on to this is a spectrometer. However, as mentioned, we do not have spectropolarimeters at all, and it is important because any signal that comes from the sun, when it passes through this different layer due to high Faraday rotation, we do expect it to be decomposing into E and O mode, and because of that, we expect some % of circular polarization. And because of, if we have a handle on this circular polarization, we can in turn estimate the coronal magnetic field. And at present, we only have a few methods to, spatially extrapolation method to estimate the coronal magnetic field. So for that, the first instrument which we are developing is ARISO. Is a spectropolarimeter. Ideally, the antenna works from almost 40 megahertz to 1 gigahertz, but we are chopping it off around 50 to 500 with back-end restriction. So the sensitivity is around 0.0 SFU at the lowest frequency and around 80 SFU at 500 megahertz. Ideally, we plan to have two modes of operation. High resolution mode where we will be having a 10 millisecond 10 kilohertz, but on a regular mode when the sun is relatively quieter, we'll go for 100 millisecond and 100 kilohertz temporal and spectral resolution. So this is how the antenna looks like. It's a cross-polarized log periodic dipole antenna. It has a moderate gain of around 7 dBi and has a broad beam as shown here. This is how the radiation pattern looks like. We need a broad beam because we are not steering the antenna, so it's a transit instrument. The sun would come in field and then go away. So this is around 70 degrees, so sun would be in field of view for roughly around 6 to 7 hours. We have some side lobes as well. Sun is a bright source, so it leaks in this as well, so we will be able to observe it. The backend is being implemented on a board called ADC plus FPGA on a together board called Radio Frequency System on Chip, RF-SOC 3rd Gen. For that, initially we are using Simulink to do the firmware design, and then we will be translating it into Vivado. So we have since we have two antennas because it's cross-polarized, so two ADCs, and then we do PFBs and FFTs, and then we do the cross-correlation and auto-correlation calculations on board, and then we packetize the data and send it to the data acquisition PC using 10G Ethernet. So the first light from this is expected to come in November this year. Recently we got some funding to deploy the same instrument but a mini version of that, so 100 megahertz to 500 megahertz at India's Arctic Research Station Himadri. So my postdoc Harsha will be going in October, November to set up the system, and then it is expected to do automatic observations in summer next year. So that was a spectropolarimeter, so it observed the sun as a star. But sun as a star observation would only tell us there is a transient that's happening within 8.5 minutes, but where is the transient happening? For that we would need imaging observations. So for that we are building a roughly 1 meter dish interferometer. So in the beginning we only have 4 dishes just to do the technology demonstration as phase 1, which would be around 20 meter up, the longest baseline is around 20 meter. The backend is, since we are again limited by the bandwidth of the backend, so we are, this works from 1 to 12 gigahertz, so we are dividing the RF signal into 4 bands, and then kind of super heterodyning we are doing here. This is the analog cartridge, and then we will be only doing these imaging observations at 4 frequencies, 4 RFI free frequencies. So we had tried a lot of antennas because our bandwidth is 1:12, so it's more than an octave. So for that we went finally, after a lot of trial and error, we set up on this antenna. It's a planar antenna, it's called a Vivaldi antenna. It's almost broadband from around 1 gigahertz to almost 11 gigahertz, except this one band is not functional. However, it doesn't fall in our 4 observational bands, so we are just as of now ignoring it. We also need to put this ground plane, and putting the ground plane has made the VSWR really bad. This has a beam width of around 70 degrees. We would need around 90 degree based on our dishes size. However, for that we would need to do some modification, but this is version 0 and it appears to be working, so we will be fabricating it soon in order to do characterization of it. So there is a poster by my student Samriddhi, so if you have some time, please go ahead and check it out. There would be more details. So again, when I was talking about single frequency observations, I mentioned how important f10.7 centimeter is, and for that we are building RFM, radio flux monitor. So the front end is being built by USO, and then the back end is being built by in collaboration with RRI. So the front end again is we plan to have a 1.2 or so meter dish, which will be commercially available. However, the tracking and controller as well as the feed is being designed by us. So this is the first version of the feed. This is a horn antenna of around 10 centimeter size, so that looks like there would be a lot of shadow on it. However, this is again version 0 of the feed. The backend is being implemented on red pitaya board, so the plan is to have for long time monitoring of the sun at this frequency, because it is important for solar cycle variability study. We want to make it as a cartridge which can be installed at multiple places in India as well. So this is the last instrument, which is we are planning to develop and demonstrate a modular instrument that can be plugged into any satellite bus. So till now all the 3 instruments are ground-based instrument, and this one is a space-based radio gonio-polarimetric plus polarimetric studies. This is in collaboration with IIT Kanpur with Dr. Mukundan. Some of you might have heard the detailed talk on the first day of the workshop, because we cannot observe less than say 10 or 15 megahertz from the ground, so we have to go to space. However, we are testing on the feasibility of this, so we are developing a lab model for this. The digital backend is in quite advanced stage. It is again for test purpose for the lab model. We are developing it on a red pitaya board. We have a poster by our student Purva Singh, so if you have time, please go ahead and check it out. So these were the instruments we are currently developing at the Udaipur Solar Observatory of PRL. However, what kind of observations we can do and how we can complement multi-wavelength observations from radio side is what I will show you in next 5 minutes or so. So again, there can be 3 kind of observations in radio wavelengths: quiet sun, active sun, and eruptive sun. And then each of these observations can very well complement multi-wavelength observation in such a sense that, for example, all these plasma properties which we observe in other wavelengths may have non-thermal components which can be very well probed using radio observations. Again, we can understand or get a handle on the bulk plasma properties of these transient sites as well as the particles which are being accelerated, how they are accelerated and how they are transported in the solar atmosphere. And there has been recent studies where people have used very high fidelity, high sensitive radio imaging instrument to comment on the coronal heating budget. So however, this radio observations still remain quite underutilized when we do the solar as well as space weather studies. So where radio observations can fit into is it can complement very well to the thermal diagnostics of these non-thermal physics with the non-thermal physics as well as this large scale connectivities, where we, as I have shown one of the images where we could trace how these accelerated particles are traveling say till 0.5 R0 or so. So again, in this type of observation, there can be 2 observations. One is long-term observation, another one is event-specific observations. So coming to long-term observations, as I have been emphasizing on the point that radio observations are quite underutilized probe. So in order to emphasis on that, we did a multiple, almost 2 solar cycle metric radio observations to understand can we comment on or how effective they are if we have a signature close to the Earth, how effectively we can comment on the space weather events. So what we found that it could be very effective estimating the coronal magnetic field close to the sun. However, this is not a very effective method to do to estimate or do things close to the sun. So we have to move lower and lower frequency, that means higher and higher heights in radio observations. Very recently, we used an instrument which is not functional anymore in Japan. It's called Nobiyama radio heliograph, where we found signatures of differential rotation as well as polar ward flows. So this is how the differential rotation at this 3000 plus minus 500 kilometers above the solar surface would look like, because we do not have height ambiguity as other wavelength observations, because radio frequencies correspond to heights and temperature very nicely. We reaffirm that how the chromosphere is rotating and this was done with some 28 years of data. For poleward float, which are very important to understand the variability of next solar cycle, this is how this butterfly diagram in radio would look like, one of the least seen images, which recently got accepted. So we found the first evidence of upper chromosphere, lowest corona, this meridional flow signatures, so which we are calling as magnetic tree connectivity. Very recently, we also studied how the polar coronal hole are related with the peak brightness in microwave, because this Nobiyama works at 17 gigahertz, used to work at 17 gigahertz microwave observations. So this movie should be playing. Okay, so what we found that they are very, very well correlated. That means these polar coronal holes are very important to study, because this high speed electron streams comes from them here. And then coming to stand-alone observations, where we do not do long term, we just pick one peculiar event. There has been theories that these radio bursts cannot be generated without coronal mass ejections. However, we have been, for the past few years, we have been trying to convince the community that it can. Anything that can generate a shock in the corona can give rise to these particular events. So we have a couple of studies in the past 2 years, and then Divya has a poster based on this where we used Aditya and solo data to understand why these, what else can produce shock that can produce these radio events. And again, what kind of instrument which should be, what should be the limit of the interferometers which we are making. So we had a study where we put a limit on the size of the radio interferometer one has to make at lower frequencies, because making an 80 kilometer baseline would be an overkill, and making a 2 kilometer baseline is not enough for us. So this study is was talking about that, just brushing through some of the glimpse of the science results which we have been doing for the past 1.5 years. Divya has a poster, feel free to go. So just to summarize everything, we have a lot of interesting developments in the solar radio instrumentation at the Udaipur Solar Observatory of PRL, and some of the science questions which we try to answer using radio observation. So thank you.
Yeah, thank you, Anshu. So we have time for questions. Yeah. No, you have to know. Yeah, you can. Here.
Yeah, so several places you are saying that the measurement of magnetic field in the corner is difficult, and you mentioned one method, that is the only method to measure the magnetic field.
Or
so the
observational.
Observation, yeah. So there's one way to measure the magnetic field is to get the phase velocity of the MHD wave and also get the density, and then you get the planar sky of the magnetic field. So how useful that magnetic field in terms of like the study that you are?
So what kind of heights are you talking about?
It's mostly in the lower corner.
So this is for middle corner.
The middle corner, right?
Yeah. So we have to, and then there is another method where we do the geometrical structure of the wave and CME as well. However, all these are for middle corona, and that is why explicitly mentioned in the middle corona that observational evidence. Yeah.
Any more questions?
So, in the figure where you are trying to see if the magnetic field obtained from metric observations, how can we use that to obtain, if we can use that to see the magnetic field change in the near Earth? So what observations were used to obtain the magnetic field for that particular figure?
So we had all the split band observations, so it's metric bursts. So we had a list of all the past 2 solar cycle, all the split band or type 2 radio bursts, and then we compared it with whatever we get at 1 AU. However, there is a big gap because since 10 or 20 AU, there are a lot of changes happening. So this study now we are trying to replicate using DH type 2 split band bursts. However, there are none. I mean, there are like 2 we found.
Okay. So I would say you can look at overall WA. There will be many. So can I ask one more question?
Yeah.
Just go ahead. Yeah.
Yeah. So what sort of angular resolution are you getting? Are you targeting for Arun?
Yeah. So for phase 1, we will have 6 beams on the sun. So 6 by 30 at highest frequency 10 gigahertz. Because just 20 meters or around 20 meter is my longest baseline, and we have 1 meter dishes. So we have to also integrate a lot in time. But this is just a technology demonstration phase. So we want to show that it can be done. And then we will be, we have phase 2 and phase 3 planned, where we will be increasing the baseline as well as the number of antennas.
Okay, thank you, Anshu. So next speaker is Shashikiran. Shashikiran Ganesh will talk on comets in the solar system. So please go ahead.
Okay, thanks. Will it work from that corner? Yeah. Okay. Thanks. Yeah. Before I start, I would like to thank the SOC of the ASI for this opportunity. It marks the 30 years of my professional career in astronomy, and I actually started observing comets in the first year of my work. So I really thank ASI for this opportunity. I think it's the first time that comets have been given this plenary stage, and it's really high time. Okay, so I will not take up a lot of time in introduction and things like that. I'll just summarize the recent results, because one of the ideas was to review the state of the field at the moment, particularly in the Indian context. Okay. So these are just a couple of images. I think you can just barely see the pointer, but yeah. So there have been a lot of people who have worked with me over the years, and we'll cover some details from the work that people have done. Yeah. This is kind of a one-shot overview or an introduction, summary of the entire work. We have it as a poster in our lobby outside, and I thought it would be good to start with this and zoom in on different areas. But it's a little outdated, so I'll just switch to the results and then we'll speak it for itself. So comets are pristine remnants from the time of formation of the solar system, and most of the time they spend their time, most of them they are at far off distances, and they become active when they move closer to the sun. Okay, and as they come closer to perihelion, the molecular emissions and other interesting features start up, and these have been of course studied since several millennia, because there were occasions when comets become bright enough to be seen even in the daytime. And if you're interested in the history, you should look at papers by Professor Kapoor from IIA. He has a big story on that. Yeah. So I said that comets are from the time of formation of the sun. And what is the evidence for that? The evidence comes from looking at the spectra of comets, especially in the infrared, and comparing them with the young stellar objects. Okay, so of course now we have much better spectra than these, but these were the first ones where we had the infrared space observatory looking at the same object, the same kind of material, one in comet Hale-Bopp and the other one in cometary in the young star cluster or stellar dust cloud they called it. This is again a more recent work where the Hale-Bopp and the HD star have been compared with the comet Temple ejecta when we had the deep impact mission. We'll go ahead. Recently I came across this nice paper which Leighton mentioned to me a couple of days ago when I met him first during this ASI. I think it will be interesting to go through this. It's a lot of infrared work that he has compiled in this. So what do we understand about comets? Okay, it's especially interesting to note the number of comets that we know so far, 4,000 comets. Okay, it's much less than the number of exoplanet candidates that we have. Okay, so I think it gives an idea where we should be putting funds, especially since comets are more dangerous compared to exoplanets, right? But anyway, that's a different story. So you have a comet, if you look at the eccentricity versus the semi-major axis plot, you can see that they are distributed in reservoirs, and this is the kind of extrapolation that one can do. In that you have the main asteroid belt here very close between Mars and Jupiter. There are active comets in this, so what we call active asteroids or main belt comets. And then you have the Kuiper belt just beyond that, and then the so-called Oort cloud even farther out. Okay, I think the observational challenge is to try and detect the Oort cloud for stars in the other for other stars. It's difficult to do that for the sun because it's too diffuse. I mean, too dispersed. Okay, based on various parameters, you can classify comets, and so far people had been talking about short and long period comets based on whether their period was below 200 years or more than that. And then we also talked about dynamically new or dynamically old, in the sense that whether they are objects which are coming in for the first time into the inner solar system, or whether they are old enough and they have come several times. Okay. Based on composition, you can talk about whether comets are carbon depleted or carbon rich, or basically carbon typical. So these are, I will come to that in a moment. Based on the dustiness of the comet also, one can talk about it as being carbon rich, dust rich or dust poor. Each of these are derived from observational aspects, and we can basically use all kinds of techniques which is available to the astronomer to study comets. Okay, but there are some limitations in the sense that comets are usually, when they're bright enough, they are closer to the sun. So we have very limited light time when you can actually observe them. They are at too low an elevation to go for observations in many of the cases. So let's start looking at each of these results one by one. I mean, how we can make use of these tools. If you take a polarization, then the scattered light from the sun is actually polarized. And this is a function of the phase angle at the time of observations, the wavelength at which you observe, the refractive index of the scattering particles, and the size distribution of the particles. So these are things which every single observation helps in understanding this. And if you, once you do that, okay, so this is just to recap that it's been 30 years since we started observing. I started observing. The observatory and the instrument had been observing much before that. In fact, the first observations were by this group from Kavalur with the same instrument, which we eventually put on our telescope later on. Yeah. So once you do the phase observations over a long period of time, you can make this kind of plots, which is the phase angle versus the polarization. And the black dots are for comet Hale-Bopp. This was one of the best studied comets available in the literature even till today. And over 50 citations to this paper from 1998, which is quite a nice record for our instrument. When you compare it with data from all other observations over compiled from the literature, then you can come up with this kind of plot where you can try and understand what kind of material is going into the in the dust. Okay, so we talk about agglomerated debris or solids, and hierarchical aggregates or rough tactical aggregates, things like that. Okay. So this can then be simulated using various codes. I think there might be a couple of slides at a later date. The second thing that we can do is, of course, spectroscopy at optical bands, optical, infrared, I mean all the gamut of spectroscopy. Mostly you see fluorescence emission from daughter molecules in the cometary coma. From the nucleus itself, we have very less signal coming out because by the time it is observable in the optical. Long chain organic material is supposed to be some of the parent material for these. So when you look at the spectrum, most of these observations and results are from the work of Kumar Venkatramani, and we'll talk about Kumar at a later point. So the typical spectrum of a carbon-rich or carbon-typical comet has a lot of strong molecular bands from C2, C3, and the strongest is the CN in the blue side of the spectrum. Most of the spectrographs that people design are for 400 nanometer and beyond, But Kumar showed that by careful calibration, we could actually use the spectrograph, even less shorter wavelengths, and get this CN band calibrated. Most comets have that kind of spectra, this kind, the one shown at the top. But there was one specific comet, Comet 2016 R2, which had spectra very different from the rest of the comets. And in fact, there's some discussion whether this could be a interstellar comet which has just seeped into the solar system. But there are simulations on the boundedness of the comet, and they show that this is not exactly an interstellar comet, it is bound to the solar system. Okay, we have a strong collaboration with the Belgians now over the last couple of years, and the first result from that was the compilation of material, observations from our telescope and the TRAPPIST telescopes of the Belgians. And here we show the first work on Comet 46P, which had multiple epochs. All these squares, the solid squares, are the data from Mount Abu and Mount Abu data. And the open squares are the photometric data from TRAPPIST. Okay. This comet is a short period comet, so there have been measurements for this comet earlier also in the literature, which you can see in the mark with the black, blue and green asterisks. Okay. And typically what we would like to study are the CN and C2 production rates, and then the rate ratios, which is shown in the top panel. This is the one which is important to understand, because that tells you whether it's a carbon typical comet or a carbon depleted comet. Okay, basically the strength of the C2 line as a reference to the CN line. Going more forward, I think many of you might recall this 2020 F3 comet, which appeared in July of 2020. It brightened up at that time, and luckily we were able to get 3 minutes of spectroscopy from there, from the Himalayan Chandra telescope. It's, I think, one of the most productive 3-minute exposures ever taken with that instrument, HFOS, on the HCT. So using that 3-minute data, we were able to actually cover, we had to organize the slit across the photocenter and also going into the new tail. So looking at the spectra, we were able to actually detect strong ionic emissions from the comet, and these are insets showing various details. One of the important points here is the detection of CO2 plus in this comet. It's very rarely reported in the cometary literature. We have to really go back to very old data sets to show that it is really present. Okay. Then the other more recent work is by Goldie and collaborators. So this is based on, I think, almost 32 months of observations using the PRL as well as the IA telescopes and the TRAPPIST telescopes from Belgium. We were able to get, I think, some 5 or 6 epochs of spectroscopy and 60 epochs of photometry. And it shows that this particular comet is actually relatively less active in terms of molecular emission, but there are signatures. What is interesting about this comet is that initially people thought it's a dynamically new comet, and we in fact even had that in the title, dynamically new comet. And but then eventually it's from our own work later on we see that it seems to be a dynamically, it's returning comet, not dynamically completely new. So that brings me to the second part of my talk. Are these comets unique to our solar system, or do we get objects from outside? So this is something which work has been going on in the literature for quite a while. And some of the recent work, the last works which people did in Ayuka, for example, Sen and Rana, Ashok Sen and N.C. Rana, these people had proposed, based on various simulations, that one interstellar comet could be there in about 2 centuries. Okay, so this was assuming various details and the level of detection capability and things like that. What has happened is that in the last 10 years, 3 interstellar objects have been discovered. Okay, one is the first one was an interstellar asteroid, which was detected as it was leaving after it had actually passed perihelion. Okay, the second one was comet 2I, Borisov. I'll just show you the details. It was discovered on 30th August by this guy Gennady Borisov with his self-built 65 centimeter telescope at a perihelion distance of 2 AU, and it had an orbital eccentricity of 3.36, really high, and velocity at infinity of 32 kilometers per second, which could not be achieved by any solar system body, so it had to be of interstellar origin. And using our Hanley telescope, and in fact even the 1.2 meter, we were actually able to get images and spectra of this comet, which is quite spectacular. We didn't expect that we would be able to study an interstellar comet, a faint one at that, using the 2-meter telescope. It was quite nice. And this comet has, this particular paper by Arvind, has received a lot of citations in recent times because of the discovery of the third interstellar comet. Let me just come back in a moment. Yeah, I think we can go ahead. So as the comet approached perihelion, the production rates went up. We were actually able to get data points before and after perihelion, and these were among the best results around perihelion because there was no other observations from this for this comet. The earlier measurements were all by 8-meter class telescopes. Our numbers show that it probably formed in a protostellar system undergoing very inhomogeneous mixing of material in the star at that time. Okay, the optical colors were redder than the solar, and that also indicated that they were similar to the solar system comets in that sense. Sana Ahmed and Kinsuk at PRL had worked on the theoretical aspects of this one, and she spoke about exocomets the other day, and she has covered a lot of ground in starting from first principles and building up a cometary coma chemistry model, and these are results from that, and if you're interested you should please talk to her about it. Pritish Haldar and collaborators have worked enormously on covering, as I mentioned, the polarization measurements. And he considers, so he has coded programs to work with GPUs as well. And the scattering simulations and measurements allow him to compute this kind of polarization phase curves and also get various other details. He considers a very range of parameters because so that's the problem with this subject is that it's a multi-parameter fit. So you need to do some kind of a simulation at with various numbers to try and fit the observations. So the more observations that you have, the better the results are. The third, I think now I'll come to the third interstellar comet, because this is the one which we have really received a lot of measurements for, and a lot of interest was there in the press because of the famous Harvard astronomer, so-called. I will not go into that detail because it's a whole talk on its own. So the comet was discovered on it was reported on the 1st of July, so that was just after the deadline for the proposal submissions. And but we were able to get some measurements nevertheless. The onset of CN emissions was detected on 12th of August, and Arvind, who did his PhD from PRL, is now in Belgium on a very competitive postdoc, and he was able to get spectra from the UVS on the VLT. Some of these observations were with 1 hour long exposures on the VLT, okay. And I think they have covered the measurements over a month across using this. More results are expected to be in press, and I think this is some kind of work that could be done and achieved with the NLOT with suitable instruments. So we should be looking at that kind of capabilities. Going further, the same kind of same comet was also observed over a much longer period, and also in detail using the studied in detail for nickel and iron emission. Okay, nickel is shown in all these red lines, and the blue marks are for the no, it's the other way. Nickel is blue, and the red ones are iron. Okay, you see them very prominently in the UV part of the spectrum, and there's a lot of interest in looking at this spectrum once it becomes publicly available. Okay, so comet with this specific comet, it came with a velocity of over 50 kilometers per hour per second. So then if you look at the path, you can see this purple line. It's going almost without any kind of interaction with the sun. It just whizzes past, okay. If you look at solar system comets, if they're coming this close, you would just see them just going back, okay. But in this case, what we realized early on was that it is going to come very close to Jupiter. So what we did was also to look at how this object would move under the influence of both Mars and Jupiter. And we have looked at the parameters, various orbital parameters, and how that changes with the close approach to these two planets. And here we show the inclination, and then this is a different plot. I'll show you, come to it later. So with this inclination, you can see that the inclination goes up a little bit after the close approach to Mars. And then the second line, vertical line, is the perihelion date. And then later on, when it comes close to Jupiter, you have different, again, a very big, strong change. Now, this strong change is a function of what kind of non-gravitational acceleration might be there in the comet, based on how the gas emissions happen. So considering that, we also looked at how close it would approach Jupiter, and that is shown in the third panel. So the hill radius is supposed to be at this point for Jupiter, and we saw that for some specific very high, probably non-plausible kind of numbers, you might expect that the comet would come much within the hill radius of Jupiter. Eventually, it turns out that it might have been closer or just beyond the hill radius. So this was again work done by Goldie and published almost very soon after the discovery of the comet. We have also carried out a lot of post-perihelion observations of this, and it was in fact the first observations from Mount Abu were the first ones to publicize that it's actually a comet, and also get the spectrum of this. And over the couple of months, we were able to cover, using both HCT as well as the 1.2 meter, we were able to cover a lot of spectra. It's definitely much more carbon rich compared to the 2I, and a lot of other numbers are coming out. It's this work is presently under circulation within the community. We'll be submitting it for publication soon. One of the interesting things about this comet was it was bright enough to be even picked up by amateur telescopes, okay, with small setups. So in fact, this is just a 130 mm refractor operated by Vikrant Agnihotri at his rooftop observatory in Kota. And using that data, we were actually able to constrain the phase. There are several options possible, but then it's possible that it might be close to this 12.8 hour rotation period. Yeah. So I suggest that this might be a good option. In fact, once LSST comes online, we will be requiring large number of telescope time to follow up on the various objects that will keep coming up. So setting up a farm of telescopes with this kind of small low-cost instruments might be a good way to follow up on these objects. There are several posters also at this ASI related to comets, some of which I just want to highlight two of them. One is by Akshat Rawat and Kinsukacharya, and they are again going forward from what Sana's work had been and trying to make a thermal model for the comet, actually for the cometary nucleus, by considering the shape that goes on the surface. Okay, they consider some different facets to the, and they started with 67P, which had really very good observations available. The second poster is by Goldie and myself. Please visit the posters, both of them are available still, and discuss with the, I think I'll stop with this summary. But the main takeaway is this, that cometary science in India is really a very subcritical domain. We have hardly 2 groups working on this, and most of the time we are involved in other details, other works as well. So we should, I think very strongly of hiring more people, and especially the younger people who are coming in. So I'll stop at this point, take some questions, and then go back to one last slide with the chair's permission.
Yeah, it's open for questions. Thank you, Shashikaran.
Yeah.
So I would, So I'm Ritavan Chatterjee from Presidency University in Kolkata. I thought that since this is a talk on comet in the ASI plenary session, some of you may be interested to hear about this historical remark, not exactly related to your work, but very much with the history of it. So in 1910, when Halley's comet was arriving, there's a lot of interest to observe it in India and worldwide. And not all of this interest was positive, in the sense that some people thought the comet's tail will pass through the Earth's atmosphere, and the atmosphere may be poisoned, and human civilization is in problem, etc. So people set up telescopes, including in Kolkata area. There's a 7-inch telescope set up just to observe this. And after the observation, etc. was done, later in 1910, an Astronomical Society of India of that time was established in Kolkata. The president was a British person working in the Treasury Department named A.G. Tompkins, and C.V. Raman was an office bearer. And it lasted for about 12 years. Then in 1922, due to lack of real scientific work that could be done, etc., it was not continuing. They also had a journal called the Journal of the Astronomical Society of India, which is archived in the digital archives. And R.C. Kapoor of IIA has written in details about that, and Rajinder Singh also in Science and Culture. So I thought that it would be of interest that comets were the sort of the reason for which the forgotten but first Astronomical Society of India was formed in India, in Kolkata. Thank you.
Thanks.
Thank you for the historical person. Yeah, the question.
I also read somewhere that after they detected CN in Halley's comet, there were a lot of sales of gas masks at that time because of this passing through the tail thing.
So this 3I Atlas spectra that you showed,
yes.
So they show quite different peaks and sometimes at the same place you see absorption as well.
Yeah.
So is this because you are looking at different phases of the comet, or is it because the environment is changing and the temperature is changing? And all?
So it's a function of, it's arranged as a function of date so it's basically as it went close to perihelion. The blue spectra are from the Hanley 2-meter telescope, and the black ones are from 1.2 meter Mount Abu telescope. Okay, and basically as you go further and further away, the spectra become noisier. So the blue spectra and the black ones, both of them, when they are close and at the brightest, then you have the strong emission lines prominently shown. The continuum has been subtracted, by the way. So you don't see any kind of absorption lines which are, I mean, the ones which are there are marked in the gray bands. These are from telluric. Okay, so yeah.
Yeah, so yeah, you mostly focus on spectroscopy.
Yeah, sure.
But on a lighter thing,
Right.
you know, from solar observations,
Yes.
SOHO has discovered 5,000 comets.
Right.
And recently, as you are working on the Atlas, there is
Yeah.
a new mission called Punch. It's actually looking
Right,
at several hundred solar radii. Atlas has been tracked for several weeks. There is a large community actually in US is working on this.
Okay, nice.
I attended the Punch Science meeting and I found out that from the heliospheric images also, you see beautiful cometary tail, they get swayed by the solar wind.
Yeah.
Sometimes they are actually, the CMEs are interacting with the tails, they get splitted into multiple pieces. So there are other kind of diagnostics one can probably do from that domain as well. So I agree with you, you know, this field is not really explored in a full strength from India, but there are multiple avenues to work on. On another note of a historical perspective, when Comet Halley came back, that was the first occasion when I was in college to get a chance to really get a handle of a telescope. So I don't know whether a pure physics student eventually got into a bit of astronomy. So that interest, the cometary things are so
It's
much
very good.
useful for outreach.
Exactly.
So I think we are not exploiting it in our fullest extent. So I think you have a point.
Yeah. In fact, Comet Halley, when 1986 was the time when I also got interested, because I made my telescope first one at that time based on a report in Sky and Telescope in Science Today. I think there's a science report or some magazine like that. So my teacher had shown me that. So that's where I made one. Yeah, in fact, I've been talking to Avik that we should use comets as test particles for the solar system dynamics. These are nice.
Yeah, there's a question there.
Yeah. Hi. So very interesting talk. And so in one of the plots in your, I think it was in the first part of your talk, you had shown where C2 and CN things you were showing. So you had shown a plot in which on y-axis you had plotted Q. So is it the Stokes parameter or it's something else?
Sorry, okay. Yeah. This one?
No.
I think this is one of them anyway.
This is one of them, yeah. So is it Stokes parameter or something else?
Yeah, sorry about not explaining this in detail, because I was running through many of the slides without going to detail. So this is actually the ratio of the production rates. It's not the Stokes parameter, it's the production rates. So we estimate them from the spectral information. And then the Q is basically that. And then is what tells you whether the comet is typical or depleted. Okay, so it's just a measurement basis for defining whether a comet is, rich in carbon or depleted in carbon. So basically, the CN strength remains strong, but then the C2 and C3 they decline.
Okay, just one follow-up question. So when you compare the dust properties in the solar system versus the interstellar medium, then what sort of different abundances do you see? I mean,
wow. Okay. Yeah. So in the interstellar medium, you expect much smaller grains to dominate, and then probably long chains as well.
Okay.
Whereas the cometary dust will be a bit more complicated to deal with. Okay. Actually, with Pritish and others, we are trying to come up with a unified model and see if we can use the same dust grains to explain both interstellar polarization as well as cometary polarization. It's not very easy to do that. It's too many parameters to fit.
Yeah. Thank you.
Yeah, you can now go with your last slide.
Right, yeah. Okay, so thanks for that, yeah. Yeah, I just wanted to take a moment to remember Kumar Venkatramani. It's been a year since he passed, and I wouldn't have been able to give this talk last year. It was too shattering. It's just a pic of him working with the very low-cost instrument that he started with. It's an instrument which just cost us around 5 lakhs for the spectrograph and then some 20 lakhs for the telescope. And he spent a lot of time actually making it compatible for science. And this is something, all of this last 10 years of spectroscopy in India has started with his work. I just request a moment in silence.
Yeah, please stand up for the 1 minute silence that is requested.
Thanks.
Okay, thank you. Yeah, I note that a comet has been named after him. It's a comet.
Yes, it's an
Yeah,
asteroid.
asteroid,
Yeah,
sir.
yeah. I was
Yeah.
happy to hear that actually. So,
Yeah, thank you, Shashikiran, and thank all the speakers this morning. Thank you.
There are a couple of announcements. Yeah. From the SOC side, so the parallel session will start at 1:45 today. Not 2:15 as we had for the first 3 days. It is at 1:45 today. Please take note. Huh? Poster session is on from the tea break, and poster session is on now. Yeah. Okay.
So there are a couple of, I think, queries. So there was a query again about participation certificate from few participants. So this will be available in your website, in your registration portal, hopefully from early next week. And ASI office will close in late evening. So those who are interested in membership, please collect form if you are going to fill in. Okay, thank you.